Even well-engineered RCC elements can develop cracks due to unseen forces, the natural behavior of materials, and real-world construction practices. There is a misconception that cracks always mean design failure.
Welcome to StructTuts, where structures speak and engineers listen.
So, why do cracks appear after proper design? There are several reasons for that, but we will discuss the most common ones causing this. The main point is that concrete is not perfectly elastic, not even like steel, which behaves elastically within its elastic limit. It creeps, shrinks, expands, and responds to its environment. Shrinkage in concrete can be categorized into two types: plastic shrinkage and drying shrinkage. Plastic shrinkage occurs within the first few hours after placement when water evaporates too quickly, leading to shallow surface cracks, especially in slabs. This is more likely in hot, dry, or windy conditions. To prevent it, methods such as wet curing, misting, using curing compounds, or applying shade cloths can be used. On the other hand, drying shrinkage happens over weeks or months as the concrete loses internal moisture. As the concrete volume reduces and is restrained by supports, tensile cracks can develop. Solutions for drying shrinkage include providing control joints, reinforcing near stress points, and using shrinkage-reducing admixtures. Creep is the sustained load deformation in concrete, where concrete under continuous load slowly deforms over time. This deformation redistributes internal stresses and may cause cracking over supports or within slabs. It typically happens over months to years. For example, long-spanning beams slowly sag under sustained load, eventually leading to cracks at the top over time. Thermal expansion and contraction occur as concrete expands in heat and contracts in cold. If this movement is restrained, such as against walls or columns, internal forces build up, leading to thermal cracks. The solution is to use expansion joints and place them at calculated intervals as per code guidelines for slabs. Differential settlement occurs when footings settle unequally, leading to bending and shear cracks in the structure. This may be caused by varying soil conditions, uneven loads, or inadequate compaction. As a result, walls or beams may develop diagonal cracks, especially near supports or junctions. The solution is to conduct proper soil testing and design appropriate footings, progressing from isolated to combined raft or even pile foundations based on the site conditions. Construction errors and detailing mistakes can lead to cracking even when the design is good. For example, missing cover blocks can leave steel exposed, which leads to corrosion and eventually causes cracks. Improper bar bending or insufficient anchorage can result in stress zones being left unreinforced. Additionally, cold joints, re-entrant corners, or the absence of corner bars often lead to visible cracking in the structure. Restraint cracks are caused by hidden internal forces. For instance, when a slab is cast between two rigid walls, it cannot freely shrink, leading to cracks near the wall. Similarly, columns surrounded by slabs on all sides experience restraint forces. These cracks aren't due to external loads, but result from internal stress caused by restricting the structure's natural movements. Environmental attack can lead to significant deterioration in concrete. Carbonation reduces the pH level of concrete, making the embedded steel more susceptible to corrosion. Additionally, the presence of sulfates and chlorides causes chemical attacks, leading to expansion and cracking. This type of damage is especially common in coastal areas due to the high salt content in the environment. Poor curing can seriously affect concrete quality. Early-age concrete needs to retain moisture to ensure proper hydration. If curing is inadequate, it can lead to shrinkage and poor strength development, resulting in microcracks and surface dusting. Real behavior doesn't always match theoretical assumptions. Most structural designs are based on ideal conditions such as uniform loads, perfect supports, and perfect material behavior. However, actual site conditions introduce factors like load misplacement, temperature gradients, and workmanship inconsistencies, which can significantly affect how the structure performs in reality. This is a consolidated table summarizing all the points we've discussed, and some new points also, showing when each cause occurs, the type of stress involved, common cracking zones, and preventive measures.